Now we're going to move on to the last property, which is the osmotic pressure. Now osmosis, before we do osmotic pressure, since you already know what osmosis is, I'm going to go over it very quickly. You know, osmosis is a spontaneous process. And what is osmosis? Osmosis is basically when water travels from area of low concentration to high concentration of solution, right? So basically, of water particles or water molecules from an area of low concentration of solution, okay, low concentration of solution to an area of, so it's net movement of water molecules from an area of low concentration of solution to an area of high concentration of solution. So basically, you can also say that where water is more, it will go from a higher concentration of where you have more solvent to an area of lower concentration of solvent. And this is going to be happening through a semi-permeable membrane. जहाँ ज़्यादा water होएगा वहाँ से it will go to the area where you have less water, or can I say where you have more water. If I have more water, it will be going from more water to area of less water. Or can I say more water basically means less concentration, because more water है तो concentration of solute कम होएगा, less water है to an area of higher concentration, right, of solution. So you can use this interchangeably. The best way to say is, I think, less concentration to an area of higher concentration of solution through a partially permeable membrane or through a semi-permeable membrane, right? So water can move in and out. If the water is going out of the body, or if it's moving outside, for example, if you have a cell, right, and the water is moving out of the cell, this is called exosmosis. And if the water is moving inside the cell, this is called endosmosis, right? So water can move out and inside, in and out of the body. If it's going into the body, we call it endosmosis. If it's going outside, we call it exosmosis, right? Now, so like right here, you can see if I have an inverted funnel, which maybe comprises of a salt solution. Let's say this has salt solution inside it, and let me say that this is what, a partially permeable membrane, and I put it in a beaker containing water. Okay, so this has water. So this is just water, right? So you have more water here, or can I say I have less concentrated solution here, right? And you have more concentrated solution inside the funnel because the salt is inside the funnel, right? So the water will be moving from an area of lower concentration to an area of higher concentration of solution, or can I say from an area of higher concentration of the water itself to an area of lower concentration, right? So water will be going from the beaker into the funnel. And you can see that because the funnel, the height of this would rise. You will see an increase in height because obviously water will be moving inside, right? And that's why you may see that there's people who take high salt diet. They have what? Water retention. We call it edema. They have water retention in their body. Why? Because you take a high salt diet, obviously there will be more salt going in your tissues and obviously more salt in your cells. So since there's going to be more salt in your cells, the fluids or the water outside the cells will start moving inside the cells. Why? Because आपके पास high salt diet में all the salt will go to your cells, and there will be osmosis of water from outside the cell to into the cell. So basically there will be endosmosis occurring if you have a high salt diet. And patients who have high salt diet, it results in a condition called edema. Swelling हो जाती है, water retention हो जाता है, right? And that is obviously because of osmosis. and this happens through a partially permeable membrane, and we know that आपके पास cells का membrane is also partially permeable. Now there's something, this is osmosis, right? Now there's something called osmotic pressure. Now what is osmotic pressure? So let's say we have these two cylinders right here connected, okay, and you have this partially permeable membrane. We call this what? SPM, semi-permeable membrane, right? Over here, so you have pressure acting on it, say. So over here you have atmospheric pressure. Over here we have atmospheric pressure, right? Over here we have the solution, and here we have the solvent. So obviously the movement of water will be from solvent. Let's just say the solvent is water. The osmosis will be occurring in this direction, right? Now, since it will be acting in this direction, you can, and if you don't want, if you don't want the movement of water from this, let me call this A and let me call this B. Obviously, there will be osmosis from B to A, right? Movement from low concentration of solution to high concentration, right? If you don't want this movement to occur, if you don't want this movement to occur through partially, if you don't want this osmosis to occur, what you will do, you will have to basically apply pressure against the direction of the movement. What will you have to do? Apply pressure against the direction of the movement. So when you will have to apply pressure against the direction, you'll have to apply pressure here. Let me call this X or pi, right? You'll have to basically provide more pressure in order to prevent this osmosis from happening. And what is this pressure? This N naught that I've written, this pi, this right here is what we call osmotic pressure. And what is osmotic pressure? It is basically the minimum pressure that you require to prevent osmosis from happening, basically, right? So this is the minimum pressure that is required to prevent movement of solvent from area of low concentration of solution to high concentration of solution. Basically, you're just preventing what? Osmosis. And the minimum pressure that you require to do that is going to be against the direction of the movement of, against the direction of osmosis. And that will be called what? Osmotic pressure. Right? So this minimum pressure is what we call osmotic pressure. And if you have a highly concentrated solution, agar concentrated solution if it's a concentrated solution, the more the concentrated solution or the more concentration of the solution, you will require greater osmotic pressure. So the more concentrated the solution, you will require greater osmotic pressure. Right? Now, how do you calculate osmotic pressure? This osmotic pressure that is required to prevent osmosis from happening is calculated by CRT, where C is the molarity. It's basically the concentration. What is this? This is the concentration. In the other two colligative properties, we were using what? The molality. Over here, you are using the concentration, which is the molarity, right? So you're going to be using molarity here, CRT, where R is the gas constant and T is the temperature, right? So you can use this to calculate the osmotic pressure. Now you use molarity here. Why? Because obviously you're dealing with liquid and measuring the moles upon, so you know moles is equals to concentration times volume, and concentration will be moles upon volume. It will be, so molarity aap kyun use kar rahe ho? Because measuring the volume of a liquid is much easier as opposed to measuring the weight of the liquid, right? So you can use molarity here because obviously it becomes difficult to measure the weight of the liquid. If you were using molality, तो आपको mass लेना पड़ता. So it's better to use volume. And that's why we use molarity here, and you can use this formula to calculate what the osmotic pressure, which is the minimum pressure you require to prevent osmosis from happening, right? Now you know that C is equals to what? N upon V, right? Where N is basically, we are using this concentration of the solute, right? So can I say osmotic pressure is equals to, concentration can be written as moles upon volume. So can I write this as N2, where N2 is basically the moles of the solute upon the volume RT, right? You know moles is what? Mass upon MR. So you can then do what? N can be written as mass upon MR upon volume RT, right? And then you can put the volume there. It can become osmotic pressure times volume is equals to W2 upon M2 RT, right? And then you can take M2 there. So it will become M2 is equals to W2 RT upon osmotic pressure times volume, right? Do you again see we can express this colligative property in terms of molar mass of the solute? And that's what we did in the other two colligative properties as well. Our formula was ending with finding M2, because this right here is the molar mass of the solute, and all colligative properties can basically be used to identify what? Proteins, polymers, etc., etc. So molar mass of the solute can be figured out, and by that you can figure out the solute because you through its colligative properties. So in all colligative properties, we are finding what? M2 in the end. Why? Because we find the molar mass of the solute, and through that we can figure out the solute itself. Now, what are the advantages of osmotic pressure over the other colligative properties? So let's see the advantages of osmotic pressure. First, this guy happens at room temperature. You do not require any temperature devices, right? If freezing point ke liye or boiling point ke liye, etc., etc., you do not require any of that. This can happen at RTP, right? So since this is happening at RTP, this can be used for thermally unstable compounds. We can use this colligative property, which can be applied to thermally unstable compounds, because you're not making use of any extreme temperatures here, right? And third, you are using molarity over molality. So if you're using molarity, it is easier. Why? Because you're calculating the volume of liquid, which is much easier to compared to finding the mass of the liquid. You're using molarity over molality, because in molality you would have had to find the mass of the liquid, which would have been very cumbersome. So you're using molarity, in which you can easily calculate the volume. That'll be easier, right? Now, based on osmosis, you all know this as well. We have three types of solutions. You can have an isotonic, you can have you can have a hypertonic, or you can have a hypotonic solution, right? So let's see those. You already know this, I'm sure. So you have an isotonic solution, you have a hypertonic solution, and you have a hypotonic solution. Okay, let's take A, and we're comparing every other solution to this A, right? So B will be either isotonic or hypertonic or hypotonic, right? So we're comparing solution B with solution A. So A is our standard, and we're comparing the rest with B with A, right? So B can either be an isotonic, it can be a hypertonic solution, or it can be a hypotonic solution. So let me say, if for example, A is my blood cell, right? Let me say A is my blood cell. So I'm comparing, let me take a salt solution, right? Because we were talking about how salt retention ho jata hai, right? So let's just take this as our salt solution. Let's take A as our blood cell. We're going to be comparing salt solutions with respect to different concentrations of salt solutions with respect to the blood cell, which is our standard A. Okay? So now an isotonic solution will be where the concentration or basically the osmotic pressure, isotonic is basically when the osmotic pressure is equal in A and B. So when the osmotic pressure of A is equal to osmotic pressure of B, we call it what? An isotonic solution. And when they have equal osmotic pressure, there will be no osmosis, right? And an example is blood cell is gonna be isotonic with the 0.9% salt solution. They are isotonic क्योंकि इनका osmotic pressure same होएगा, there will be no net movement, and आपके पास this is seen with blood cell and 0.9% NaCl. A hypertonic solution would be where the solution has greater osmotic pressure compared to the other one. So if I say B will have a greater osmotic pressure compared to A, right? So you will have a hypertonic solution will be when the solution with greater osmotic pressure or concentration compared to the other solution, right? So in this case, sorry, I think I wrote B is greater than A, where A will be greater than B. सही है? So the osmotic pressure in the blood cell is gonna be greater than 0.9%. If you have, so basically now when you had blood cell and 0.9%, they were isotonic, right? But now if I take NaCl, which is greater than 0.9%, right? Not 0.9%, but if I'm taking greater than 0.9%, then I will call this a hypertonic solution. So if I have a hypertonic solution, in that case, my red blood cell or a blood cell, whatever, will shrink. Right? When placed in a hypertonic, जब आपने isotonic में डाला था, when you placed it in 0.9% NaCl, nothing happened. There was no osmosis. But when you place it in a hypertonic solution, what's a hyper? Hyper means more, right? Like hypertension. So yeah, hypertension means more. So when you have NaCl, now you have NaCl which is greater than 0.9%. So yeah, so when you have a hypertonic solution, in that case, what will happen? Your cell will shrink. So when you place it in isotonic, nothing happens. When you place it in a hypertonic solution, what is a hypertonic? It will be greater than 0.9. So yeah, NaCl solution greater than 0.9. So that will be a hypertonic solution. In that case, your cell will shrink. And you can have a hypotonic solution. Hypotonic kya hoga? Hypotonic will be when the concentration of the solution B. So over here, basically, my solution B is greater than 0.9% NaCl, right? Now, if your B is less than 0.9, hypotonic, kam hota hai, so that type of a solution is called what? Hypotonic. In that case, what will happen? Your cell will swell. So if you put your blood cell in a hypotonic solution, cell will swell. If you put it in a hypertonic solution, kyunki dekho what will happen. I'm sure you all have already made sense of this and you know it. When you placed it in a hypertonic solution, ठीक है, तो hypertonic solution में जब आप डालोगे तो ये आपका cell है और बाहर आपके पास क्या है? Greater than 0.9, right? Greater than 0.9% NaCl. You can take any value. Let's just take any, like 3% or whatever, I don't know, right? So when you place it in a hypertonic solution, so this is more concentrated, right? And the cell will be less concentrated, right? Let me just take this as 2% NaCl, okay? So do you see that this outside environment is more concentrated, this is less concentrated? So the movement will be outside the cell, right? It will undergo what? Exosmosis. It will undergo what? Exosmosis. It's going to move out. And because of exosmosis, the cell will shrink. But if you place it in a solution which is less, let's say 0.5% NaCl in a hypotonic solution. तो hypotonic solution में अब here your concentration is less, right? And here your concentration is more. So your movement will be inside the cell. End osmosis hoga. End osmosis hoga, so your cell will swell, right? So this is, I think you already knew this. So this is done. Now let's see the application of what we call osmotic pressure or osmosis. This is used for purification of water, right? So we can use this for purification or desalination of water. And the method we use is called reverse osmosis. So this is helpful for purification of water. How? Let's say we have this right here. So we have a semi-permeable membrane here. On this side of the tank, we have salt water. On this side of the tank, we have fresh water. And when you have salt water, can I say the concentration is high here and the concentration is less here? because वहाँ पे ज़्यादा concentrated है ना, यहाँ पे मैं लगा देते piston, right, to change the pressure. This right here is your piston and this right here is your semi-permeable membrane, okay? And this right here is your water outlet, okay? Now you'd expect, obviously, since this is higher concentration, this is lower concentration, let me call this tank A, tank B. You will expect that our water should move from A to B. That's how osmosis should take place, because it goes from lower concentration to area of higher concentration. That's what you would expect, right? But what will you do? You will apply pressure, right? And I told you, when you apply pressure to prevent osmosis from happening, that is called osmotic pressure. अब आप यहाँ से pressure apply करोगे, ठीक है? अब आपने अगर osmotic pressure apply किया and दोनों में pressure same हो गया, तो there will be no net movement. ना तो B से A में जाएगा, ना A से B में जाएगा. But now if you apply so much pressure, even beyond the osmotic pressure, there will be what? Reverse osmosis happening. What will happen? Reverse osmosis. So first step was you were expecting osmosis to go from A to B, but that does not happen, because what do? You apply pressure, right? But then you apply so much pressure. Yeah, you apply so much pressure. When you apply pressure, this does not happen, right? So this is part 3. First step was you were expecting this, did not happen, because second step you applied pressure. You applied pressure from A to B, the movement stopped. That was step 3. And now you apply so much pressure beyond the osmotic pressure that there will be reverse osmosis, and there will be movement of solvent from B to A. This happens. And why does this happen? Because you have applied so much pressure. Now there will be movement, or can I say there will be reverse osmosis. And this is not a natural phenomena. Osmosis was spontaneous, it was natural. This is not, because you're applying pressure, right? So now what will happen? That there will be water movement or movement of the solvent from B to A, and it will leave the solute in B. Solute will stay here and water will move in A, right? And you can obtain water from that. Say, so this is the application of osmosis. It is used for desalination of water. And is used in areas where you probably just get water from rivers and lakes, and it's only salt water. So you can do desalination or reverse osmosis through applying extreme amounts of pressure, and you can get fresh water, right? So this right here